Rolling.
Okay, here we go.
Well, as I live and breathe, and somehow all five of us still are, it's the SBAU Astro Hour, everybody. Weekly Monday morning vlog podcast for the Santa Barbara Astronomical Unit. I am Ronnie Heron, your host for this event, number 266 program,
Okay, go.
as we plunge into our sixth year of covering cosmology in cutting edge chunks. Our club's president, whom I'll introduce you to in a moment, came up with this idea this morning YouTube show, following about 4 or 5 years on the radio back in the 20 teens, over half a decade ago. And he sends us these items to talk about 6 or 7 topics a week and becomes a professor of astrophysics. We meet at the Santa Barbara Museum of Natural History. In fact, we are this Friday night for the first Friday. Dr. Malkin from UCLA takes us on board his many hours on the Webb telescope. Now let's go to the topics of the week. Wednesday, April 1st, brings a full moon called the pink moon, just after 7. And it's also the date NASA will return us to the moon, even though we're not going to land 4 Americans. All astronauts on Artemis 2 rocket are set to take off from Canaveral, go way out beyond and come back. Next time, maybe we'll land. We also have the constellation Corvus the Crow, directly opposite the sun and above the horizon all night long. Spaceships are getting heat shields to enter other planets' atmospheres. I know of one. Lots of friction out there, just like re-entry here. And we got time to talk about time. We're going to take the time. It ain't written everywhere, and wait till you hear how quantum mechanics figures in on it. Now, to focus this week on Vega, once and future pole star, sorry, Polaris. And then there's NGC 2301, the great bird of the galaxy star cluster. Let's meet the crew. Here's our Santa Barbara Astronomical Unit President, Jerry. Got a very big family. Jerry Wilson, married to
Good
Pat.
morning. Good
Hi.
morning to my sister Joyce and my grandkids, Riley and Calvin.
Okay, also married to a Pat as our outreach coordinator, incredible Chuck McPartland, who's still on the go, showing no end in sight. Have telescope will travel. Call us if you want us anywhere. We just, I guess, lost the hotels, but we're still at the state parks and the schools, aren't we, guys? And he's married to Pat McPartland, our merchandise manager, and as well as our treasurer. Look who joined us, Tom Whittemore, editor of our newsletter every week,
Morning.
former Westmont professor, and also an active birder for the Audubon Society. He's married to the lovely Maureen. And here's a guy that's going to be delivering a speech to us, a science talk in December. He's working on that, Tim Crawford, who's married to Karen. And most of these guys can be caught in the sunshine on Sundays, looking the only place you can look during the daytime with your telescopes, using a filter at our beautiful museum. And we'll see you this coming Friday night. We start the show. This will be number 266 with Silly's forwarded silly science tunes and a lot of stick figures in this group today, including the truth behind single star maps. So that's not what this is. Okay, you're going to have to expand that and talk about it, Jerry.
Okay,
Thinking in here.
this is a graph that shows the time spent debugging centimeter wavelength antennas. And this is versus the Nobel Prizes awarded as a result. And this is people that work on their antennas but don't get a Nobel Prize about it. And out here, there was one case back in the 50s or 60s where two guys, Penzias and Wilson, were cleaning their antenna, even down to scrubbing all the pigeon poop out of it, because they couldn't get rid of this persistent background humming sound. And as a result, they discovered the cosmic microwave background, and they got a Nobel Prize for it. So
Those big radio antenna that lay on their side that you could crawl into.
the what?
They kind of lay on their side. They're strangely shaped.
That big antenna was on its side. Yeah, it was like a big
Like a horn.
old hearing horn for
Yeah.
people before they invented electronics.
Yeah.
And when you, back in the 50s, in your black and white TV set, if you went between channels, you saw all this static in there.
Yeah.
That is also the cosmic microwave background. You're listening to it, but nobody knew that at the time.
Yeah.
So they gave us that modeled big oval of the blue and yellow splotches everywhere. Is
Yeah,
that
that's it. That's a map of the temperature profile of the cosmic microwave background. This is just listening to the buzz.
Had I only known then.
Yeah, that's right.
Right.
I've
There's
always
a whole
wondered
bunch
why
of
we don't
those in
see
physics.
why don't we see spikes of little dots where the stars would be? They'd certainly generate a lot more than the
There are
background.
no stars at microwave backgrounds, at microwave wavelengths.
I used to tell you, what are you watching? Nothing.
Yeah. So here's
Okay.
another one. Aren't you worried these will be disruptive for our ground-based astronomy? No way. This guy's putting up a 100-mile wide billboard in space with very bad maps of the stars on it in front of the stars. And this may be a cartoon now, but people are actually proposing to do this.
And
Oh,
putting
well,
up mirrors.
Yeah, mirrors too.
I
Wow.
thought maybe this was about those terrible little maps that Chuck hates.
Oh,
No,
those.
those aren't in space.
Yeah,
Oh, I
no,
see.
not yet.
You got it.
They're going to put mirrors up there?
Yeah,
Yeah,
there's a company that wants to sell light to
Yeah,
places that don't have good lighting.
Well,
yeah.
maybe they'll end up with a solar cooker.
Yeah.
Hey, Tom Whittemore, you were a science instructor at Westmont. Why don't you go through this? Chemistry's
Oh,
awesome.
okay. It says chemistry is awesome, and it looks like has a series of benzene rings. So upper left is chocolate. Okay.
Is that about chocolate as a molecule?
Yeah.
Yes.
Yeah, yeah.
Really?
Look at the caffeine.
Good Lord.
Pretty wired.
That's how I look. That's how I
And
look.
it's look at it, it's very similar.
It's like, as far as I
Yeah.
can tell, it's identical.
Except for the red and the yellow exchange.
And similar to adrenaline at the bottom.
You see the red and the yellow. Let's see. Yeah, it looks exactly the same.
Except for that extra little yellow sticking out from the left eye.
That's it. Yeah, that's it. Okay, then there's alcohol, ethanol. Okay, and looks like somebody's enjoying a glass of beer. And then there's happiness, serotonin. Okay,
Yep.
then there's love, dopamine. Look at the eyeballs.
Yeah.
Yeah, right.
Yeah.
And then adrenaline. Look at that. Somebody on a surfboard.
Epinephrine. How many of those are organic?
All of them.
I think they all are.
So they all have carbon in them, in other words.
Oh, yeah, you're right. There is a yellow one that sticks up to the left
Yeah.
Yes.
on the
Uh-huh.
eye. That's not, yeah. Okay,
What do you
good. I'm not going crazy.
Pretty good.
I didn't get that, Jerry, but that's all right. More stick figures are us. So Chuck, why don't you get us through this one?
Okay, this if you've seen Project Hail Mary, I was able to produce artificial gravity by rotating the ship along its longitudinal axis, helping passengers maintain muscle mass on the long duration voyage. But the cruise line fired me.
Only works in space.
Yeah,
So that movie you saw is about that. It's about using
several
What-
movies have that,
Yeah.
Mhm.
this is a
including
big-
2010, A Space Odyssey, things like that.
Okay, you're right. Okay, Jerry, this one.
Well, this is more of just a sage saying, the sun provides energy and light. The moon plays a role in providing proper climates. Jupiter and Saturn protect us from asteroids and comets. The solar system is not just any star system. It is a family.
Oh man,
So there should be an extra term in the Drake equation for this.
Yeah.
that's supposed to be a nebula.
Now, this is really interesting.
Yeah,
This
I
is
like it.
This is futuristic movie timelines. That means that in the movie, for example, The Running Man, it takes place in 2017. So here's all these science fiction stories listed by the years in which the plot takes place.
Mhm.
And right here is where we are between
Actually,
Blade Runner and Soylent Green.
actually, we're a little past that.
You're right. You're right.
Yeah.
Children of Men and Soylent Green. And where was it? There's one, I saw a picture of a memorial in somewhere like Iowa, and it said the future site of the birth of Captain James T. Kirk in 2033.
They actually put that in the show.
It wasn't in a show. It was just
They
in the
give
show.
them
He talks about when he was born and where one time.
What does it mean for those bars to go left?
It's nothing.
I mean, would that be the
The book is not longer or shorter.
It might be when the book was written.
Oh, I see. Got it right. Do you suppose back in the 20s they did a science fiction called Metropolis?
Oh yeah, that's not on here.
That's not part of this, huh?
That movie, if you ever seen that Idiocracy, that is hilarious.
Yeah,
I
it's
had no
scary too.
Yeah.
Yeah.
It's too close to reality these days.
I love the lawyer in it. He got his license from Costco.
Yeah. That's coming when they get rid of the Department of Education.
Yeah. Yeah.
Well,
It's a good
Wednesday,
movie.
you think we'll get to watch Artemis launch? What time of day is that supposed to be? Does anybody know?
No, I don't.
Well, 80%
Now
good
this
weather.
is a good colorful picture with a lot of pink in it, because the full moon this month is a pink moon, which happens on April 1st. And but this is of no astronomical meaning. It's just that it's a good picture of the moon and pink.
Yeah.
You're
Looks
kidding,
like
though, right?
Looks
What?
like an apple tree.
You're
Looks
kidding.
like-
It's April 1st, though.
Should be
Yeah.
the April Fool. Should be called the April Fool.
That's a tricky thing to talk about, isn't it?
Yeah.
Yeah, it is.
Now, how
It's
about
also-
Artemis 2? Is that April 1st?
Yeah.
It just turns out April 1st is Passover too.
Okay.
But
There's
Beginning of
another
Passover.
pun, Tom.
Yeah.
that's a day we don't believe anything because of April Fool.
So Tim, this is Izar.
Yes.
It's a star in
Mhm.
Ventus.
It's a hard one to crack, Jerry. You ever crack that one?
Crack it?
Yeah, split
No,
it.
no.
Split it. It's got a green companion.
Uh,
It's
the-
a tough one to split.
And this is the moon tonight. No, the April 1st at 9 o'clock. There's the moon, the full moon.
Mm-hmm.
So this is the time of the month when you look for star things that are bright. You don't look for nebula.
Or
So
galaxies. Yeah.
for galaxies. And this
There it is. There it is.
Good
is a
grief.
picture.
I've cracked it.
Izar.
I've cracked it with the refractor.
Wow.
And
I swear it's green.
that looks blue to me.
Yeah, not in my scope.
You might want to
Yeah.
clean the scope.
So is that just a trick of color, Tom, that does that?
Yeah.
The green
Yeah,
color is
yeah.
just a trick of your eye.
Yeah.
Yeah.
It's a pretty close pair.
Yeah. There's a couple that look like they're green stars. I think it's
Mhm.
Antares that has a companion.
Yeah,
And the
there's
companion looks green to some people.
there's one in Hercules too, I think.
And in Libra, right?
Okay.
I
Okay.
might have told you this trick one time that we did in the dental lab to get with color, where you draw a circle,
Mm-hmm.
you draw a circle, then draw another one and fill it with red, and stare at the red circle for a long
Oh,
time,
yeah.
and then switch over to the one with just the circle around it, and you'll see the complement green.
Yeah.
And it's just an amazing trick. It really works. So I would imagine that that's exactly what happened here.
So it's a binary, huh?
Mm-hmm. Yeah, close one. Pretty close.
I guess so. My God.
We got to try that one, Tom, soon.
Mhm.
Here, two of them are making love.
You need a pretty good steady night, Tim. But what do you have? 101, 102? That'll do it.
Yeah, the 101 might be a really good choice.
Mm-hmm.
Just a second. I'm looking up a comment here.
Okay.
Its name comes from the short Arabic phrase meaning girdle or loincloth. and means much the same as Mizar, which is Izar, but with an M on the front of it.
Yeah,
That
yeah.
indicates loin in Ursa Major.
Yeah, I've always heard that Mizar meant something different in Arabic. So we have to get an Arabic speaker.
Yeah.
Okay. Don't we have a couple in the club?
Yes. Was it Fahar?
That's who I'm thinking
Ibrahim
of.
Arshad
Yes,
Marmy?
yes.
Yeah.
Farshad is
Farshad.
Persian.
He's Persian. Yeah.
Well, that's Farsi they speak.
Yeah.
It's Farsi. Yeah.
So
Wonder
maybe it's,
how he
I don't
feels
know the
about it.
relationship of those languages at all.
And what was the nickname of this, Jerry? I found that was interesting.
It was called,
Pulkarima.
yeah,
Yeah. Pulkarima. The most beautiful.
Yeah.
these
in
are,
Latin.
these stars are 3 seconds of an arc apart. That was what I was looking for.
Yeah. Yeah. Okay.
With an amateur scope, some sea level here, um, I really can't resolve, due to seeing, I really very seldom can resolve anything down to 3 seconds of an arc.
Mm-hmm.
Well, is it called Izar or Mizar?
Izar,
That's Izar. Izar.
Mizar is the one in the Big Dipper, Ron.
Right.
Yeah, when you asked me this yesterday, Jerry, I was thinking, I wonder if he's talking about Mizar. And then I said, no, I've heard of this, but where is it?
Mhm.
And then that's interesting. I'm gonna try and go there.
Mhm.
And usually when people talk about Arabic phrase meaning girdle or loincloth, they're talking about the three stars in the belt of Orion.
Right.
Really?
And they don't sound anything like this.
No. Al Nitak, Al Nilam,
Mintaka.
Mintaka. Yeah.
There's probably a really good double coming up around the 18th in Corcaroli. That's another one.
Yeah, that's an easy one to crack. That's a nice cloud freezer.
Yeah.
Looks
But
like
with
car
the-
headlights.
Yeah.
with the
Yeah.
possible the exception, gentlemen, of Alpha Centauri, don't most double stars have one name between them? Both stars are named the same, or only the big one? Because Alpha's got Proxima, and I think we named all three stars.
Well,
Alpha.
it depends whether you can split them visually or not.
yeah, these were named before telescopes generally, if they have a proper name.
I see.
But what is it? Centauri, Proxima, Alpha Centauri is triple star system, and so the refers to all of them.
But Proxima is the closest to us. It's
Yes.
Yeah,
the red dwarf. But isn't
Now,
it
this
orbiting
is-
the bigger one, and it will go away from us, and then the bigger one will be close to us?
Well, the bigger pair will end up closer to us.
Well, it orbits two stars.
Yes, it's a triple
It's a-
system.
yeah,
Wow.
and two of them are a little closer together than the third one.
And-
So this
and
is a small constellation. I believe it's number 70 out of the 88 total constellations there are. It's the Crow, Corvus. And in it is the antenna, which I didn't show, but M104, the sombrero is in here.
And I like it doesn't look like a crow to me. And I like the Polynesian version, which is a mast and a sail.
That's what it
Yeah.
looks like to me.
Yeah, the sail is what I've always heard.
And
it-
also in the modern consumer society, it's the great shopping cart in the sky. And Algorab up there is a double, so that's that wobbly wheel on your shopping cart.
Yeah. And Jerry,
Oh, there.
the star hop I was talking about is Epsilon. How would you say it? Corvi?
Yeah, Corby.
Oh, you got it. Yeah, there it is. There's that star hop. But that Alchiba down below, if you line that up with Algorab, it's almost dead on.
Mm-hmm.
But the ones you really see are those two. Those two, that Algorab and Epsilon Corvi. And in that little square there, where 104 is, I think that the little star to the right may not be it, but there's an arrow
Right.
that points directly to 104.
Yeah.
And
And
there's
what
a close-up Jerry has that shows that.
Oh, good.
Now remember this star, and then these four, are these four in a photograph
Oh, wow.
of the constellation. It's quite a nice one.
Mm.
This was, let's see, corner of, oh, well, it's a hard name to read, but it was taken from a laboratory, from the NSF group.
So Corvus means crow in Arabic.
Yeah, nice picture.
In Latin.
It's a Latin word for crow.
Oh, there's the double you were talking about. Is it Algarab? Is it up in the upper
Yeah.
left there?
Yeah. That's the wobbly wheel.
Up there.
No, no, down.
Down below, right there.
Yeah.
That's pretty good.
Okay.
The wobbly wheel.
Oh,
Boy, there's a lot of those.
And Ron, if you're interested, the Polish word for crow is kruk.
is what?
Kruk, Kruk, kruk. There was a baseball player for the San Francisco Giants whose last name was Kruk. And my mom said, he's a good boy. He's Polish.
A lot of people feel that way about crows. They're crooks.
No, Kruk, Kruk, Kruk.
So this shows a closer view from the planetarium software of the Sombrero Galaxy.
Mhm.
And the jaws up here and the Stargate over here. Now, this is the kind of, when I operated to find something to take pictures of before I knew how to plate solve, I would make progressively closer in printouts from planetarium software that would show the stars around it and the object. Because in general, in a finder scope, you can't see the Sombrero Galaxy, so you have to see the pattern of stars around it and then center on it, and then you take a few frame and focus shots real quick to see if you got it, and then you will take an image, and I take an image of it.
Yeah.
So this is zoomed in a little bit.
And that triangle below it, I think, is your arrowhead.
That's your arrow. That's right, Chuck. That's the arrow.
Oh, is that the arrow there?
Yeah. Mm-hmm.
Okay.
Where I don't see an arrow.
Right
It's a
below
little
the sombrero,
triangle,
the
Jerry,
triangle.
points up and
Oh,
to the left.
those stars?
Yeah, that's the
Yeah,
one.
and then there's a smaller dim one down below that kind of is the shaft.
Okay. That's a right triangle.
But it's amazing that when you find that, you may not see the sombrero, but if you can really see that arrow and the little
Oh, yeah.
and
And
the
also the
voice.
Sombrero has some very nice stars for tracking on around it, which a lot of galaxies don't have.
Yeah.
And that Stargate asterism is pretty cool too.
I need to get a picture of that. We'll do that next time.
Mm-hmm.
I've never heard of that.
So this is the Sombrero Galaxy.
Really blown out.
Okay.
Yeah. And again, I keep saying this. I saw that in a 61-inch Tucson.
Wow.
It was amazing.
I saw it in a 48 at RTMC. That was pretty cool too.
Wow.
It was a corrected Dahl Kirkham, and it was about the size of a Volkswagen bus. There it is.
Yeah.
Yeah, the 61-inch is in the same, I think it's in the same area where Adam Block does a lot of his stuff up in the Catalinas above Tucson.
Hmm. Every time you say 61-inch, I think of Mount Wilson.
So Adam uses a smaller scope. He doesn't use a 61.
No.
You know, the 61 might have been the telescope they used. It was on a special axis to research areas on the moon in the 60s, 50s,
Uh-huh.
60s, where the astronauts might land. And so you can't get a lot of the sky with it. It's really pinched. Its point of view is pinched.
And also the Carroll scope that used to be at Westmont
Uh-huh.
was built by George Carroll, but it was a prototype for a 36-inch or 33-inch that he built.
Mm-hmm.
That's up at Stony Brook Observatory or Stony something up by the ski resorts near Big Bear. And they use that to survey the moon too.
Okay.
Now, this galaxy is reputed to be 9,000 times more massive than our Milky Way.
Wow.
So
Or the black hole in the center, yeah.
Yeah. Yeah,
And
that's
there's a cool pair of twin spirals down there at like the 7 o'clock position.
Yeah. Yeah, there's a lot of distant stuff in this image. Even in the upper right corner, you see a cluster of galaxies.
Mhm.
Yeah.
yeah,
That's an amazing shot.
yeah. Does
And
it
I
say
saw
what it's
somewhere
taken from?
an estimate that this galaxy has like 30,000 globular clusters.
Yeah.
Holy crap.
Hmm.
Oh, the caption does not say where it was taken from.
Mhm.
I think that's a Hubble.
It
Yeah,
looks
it's
like it. It's
got
very highly detailed.
all the distant galaxies it's picking off.
Yeah.
Well, the star parties would be really long if we lived there, Chuck.
Yeah.
Oh, all this light out here, the haze around it, those are all stars, star
Yeah.
clouds, very open, loose star clouds.
The haze is?
The
Yeah.
haze, yeah,
Wow.
unresolved stars.
But this thing was bright enough for Messier to,
Yeah.
list it, see it.
And why do we have a dark ring on this side?
And nearby to the sombrero is the Southern Owl Nebula.
Hmm.
And this is a shot of it from my planetarium software, the Sky 6. And this is a shot by, let's see, where is that?
Wow.
This is a shot from the very large telescope in northern Chile, European Southern Observatory.
Looks like the Bubble Nebula.
Hmm.
Yeah, it looks like a bubble. It also has got two faint things like eyes, so it's called the Southern Owl.
Yeah, it looks more like the Southern Duck. Look at that beak.
Yeah, it does. Staring straight at us. Yeah.
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 Huh.
Okay, we're going to go to a little technical stuff here. Arrow braking.
This one was interesting.
Now, we're not going to go through all this reading stuff, but this is used for landing on places that have an atmosphere. And the problem is that we use it, of course, to re-enter spacecraft to the Earth, and that works pretty good. We have a succession of parachutes, high-speed supersonic parachutes, and then drogue chutes that slow it down, and then the weaker chutes, but big area that bring it down to about 30 miles an hour to land on Earth. But the point of this is that, as you know, on Mars, it's a little tricky because the atmosphere is 1% the density of Earth's atmosphere, but it is CO2. And so we used a combination of aeroshell to get through the upper atmosphere and lose its 12,500 mile an hour speed and bring it down to where high-speed parachutes could then operate past the region where the heat would cause them to melt or rip apart. And then on Mars, because the atmosphere is so thin, we have to use rockets to do the final thing. Early on, we used airbags for Pathfinder and Mars Exploration Rover, and they just pop out, and then the thing bounces around, and where it stops, you find out later. A couple of them did deflate, but it didn't really jeopardize the mission. And for the latest ones with the biggest rovers on them, we use the Sky Crane, which is a decelerating retro rocket platform that then lowers the rover down on the cables. And that's great. Whoops. Oh, this thinks it's the last one. I got to change the method here. Okay. Okay. Now, oh, yes. This might be problematic too. This shows how we change the speed of a body by sending it with, this was actually a Mars Maven, I think it was. that comes in here, and it has to it's approaching here. This is the start arrow in a hyperbolic approach, and it hits the atmosphere at just the right angle. If it hits too shallow, it'll ricochet off and be gone forever. If it hits too shallow or too steep, it'll burn up. So you just skim along the upper regions of the atmosphere, lose some speed, then it pops out its solar cells, and it comes into the region where they want to be in an orbit. So it fires its orbital insertion, and then it ends up in this desired orbit. And that's what we've been using for aerobraking.
Good
And
grief.
this is a image of two capsules landing on Mars in parallel. I would have expected, I looked for one that had Starship, SpaceX's Starship on it, but I couldn't find any. So nice picture though. Anyway, what we just discussed was the Maven, which was a orbiting spacecraft for Mars. And as we said, it goes and dips in deep, 125 miles. And these things are done quite precisely and gets it into from a relay orbit with about 3.5-hour period. Now, this is all done with Newtonian dynamics discovered and published in 1666. No quantum mechanics, no general relativity is required on this. So this is how accurate Newtonian mechanics is for this scale and time frame. This is
Get that angle of descent right is just mind-blowing.
it's precise.
And they had to do that for the Apollo missions coming back from the moon.
Yeah.
Mercury and Gemini, yes. Oh, when they re-entered from orbit, yes.
Yeah.
And this is the Dragonfly capsule, a successor to the one on Mars, which was called what? Firefly? No.
Integrity or something like that?
Yeah, Integrity, that's it. So this is there's a nuclear reactor on back. You can see the tail out there for power. It's got 3 or 4 rotator posts, and there's two blades on each end of the rotator post. So there's 8 what do they call them?
Rotor discs, yeah.
Rotor blades, yeah. And this is with a background apparently of Mars. So it is being considered for Mars. And
No, this is for Titan.
yeah, I'll get to that.
Okay.
Yes. And it's also being considered for Titan, which has a much thicker atmosphere, and for Venus, which has a much thicker atmosphere.
Ooh.
So, but the trick is they're finding in studies that they did with this, they found that the way the material, you know how ablation shields work when they're aerobraking, the material has a very low thermal transmission rate and a very high thermal capacity. So the outer layer of the ablation material gets very hot, but the heat does not travel well through the material. So the outer layer then becomes also weakened by the heat, and the rush of air past it, or the atmosphere past it, blows it off. So it carries the heat away, and that cools this thing down. The problem is
You can't use it again, huh?
No, you want, yeah, there's a junkyard with used heat shields. Don't, that's like a retread. Don't.
Yeah.
Yeah.
So they're studying different cone shapes and in different atmospheres in wind tunnels. It turns out with oxygen in the atmosphere and nitrogen, they work pretty well. But places that they want to look, such as on Titan and on Venus, the atmosphere is different, and the ablation system does not work the same way.
So Venus just melt.
Yeah. You don't want it to not work. So they're looking at it, the article I got this from, they're looking at different compositions of atmosphere and determining, they're designing the heat shields now for re-entry or for entry into the atmosphere to get the rope, the, what is it, the flyer, the helicopter into the atmosphere. But we're going to see missions of those probably within the next decade.
Just out of curiosity, Jerry, when they make these heat shields, is there a common denominator material that they use, they start with?
I don't know the answer to
These
that.
days, carbon fiber.
Really? Huh.
What do you suppose Russia used for their old Veneras on Venus?
Venus, I don't know. Good questions, all.
Something that won't melt.
Yeah, well, what you want is no thermal conductivity, a thermal insulator like a ceramic or something, but something that breaks off easily when it's hot.
Hmm.
Can take the heat away.
That's why when meteorites land, they're often, within 15 minutes, they're covered with frost
Oh,
because they ablate away and that takes the heat off.
yeah.
Really? Well, this is a great picture.
Now, this is a weird thing that I had AI generate, or rather, AI offered to generate it, and I accepted to see what it would do.
Huh.
And the article I wrote for the newsletter took me quite a while to write it, getting it all straight in my head. And I had Gemini look through it mostly for typos, which it found a bunch of them. The double slit experiments became the double kit experiment. But it's useful for that. But then it said, you want me to make a graphic? And I thought, sure, what the heck? And so this is what it came up with. And what I was talking, it gives something good in the background to talk about the time. I was trying to explain how we have evolved our vision of time over ages from ancient Marcus Aurelius, who talked about time as being an infinitesimally thin region between the past, which is gone, and the future, which is not here yet. And that was the way people thought of it, and even embodied in Newtonian dynamics, that the time is something that is the same. It's rigid. It's absolute. The time for you and the time for me and the time on Jupiter and the time on Andromeda is all the same time. It passes at the same rate, and now is now. And then in the early 20th century, relativity got rid of all of that. Time is no longer absolute. Time is relative. It's relative to where you are and what you're doing. If you look, when viewed from an outside viewpoint, for you, no matter where you are and what you're doing, your watch will always look the same to you. But to someone in a different frame, stationary with regard to you zipping by on a spaceship, your time will be going slower. And if you're in the space between or near a very, very massive object, time will be going slower as viewed from someone who's outside of that situation. And that's, of course, the plot line of the movie Interstellar, where this 10-year-old girl tries to talk her dad into not going into space near a supermassive object. And he goes there and he spends a couple of weeks there. And when he gets back, his 10-year-old daughter is a dying grandmother in her nearly 100 years old because of the time difference, because they were in different regions. And Einstein referred to it as a stubborn illusion.
And, with really accurate atomic clocks now, you can measure the difference in time flow between like the bottom of Stork Tower and the top of Stork Tower.
Right, because you're closer to a massive body. And our GPS would not work if we didn't apply general relativity corrections, because the satellite calculating where you are is farther away from the massive Earth, and it's going faster than you are on Earth. So it has to do these corrections to get it right. Otherwise, it would be off by a mile or so, and it would be useless. Now, quantum mechanics also makes things even weirder, is that quantum mechanics doesn't deal with, Newtonian dynamics deals with particles, and it's deterministic. You can calculate where your spacecraft is going to be when it gets to Mars, and you can figure out how to get it so it lands on Mars when Mars gets to that place. quantum mechanics working in the subatomic region takes individual particles, but it does not calculate the deterministic path of that individual particles. It gives you the wave function, which is the probability density. And so from that, you can turn that probability density into a particle that is deterministic in the past. And that's what quantum mechanics defines as the present. So you're looking, and it reminded me of this lyric from a song. Time, 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 see what's become of me while I look around for my possibilities. So that's how we view time, is we run into all these quantum mechanical possibilities, and then we make a decision, say by viewing it, observing it, or by choosing to do something, to get out of bed or not or something. Now I'm mixing particles, subatomic particles, and macroscopic events, but the idea is the same. And so, and then in the past, then everything is deterministic because you've made a decision, and now the particles have deterministic paths. So it got me to thinking, the reason I was trying to think of this was, suppose time travel is possible, which I suspect it's not. But if you went into the past, to your own past, would you find that you were now in a world made of all the observation and choices that you made, and you would be bound to make them again? Or would you run into, or would it become a new present where now you can make new decisions or not? So I have several different ways of giving myself Excedrin headaches, and that's one of them.
Well, it's certainly been kicked around a lot in sci-fi.
I read too much of that.
Yeah.
God, there's bad sci-fi out there. This is
Ahead of Tycho.
oh yeah, this is about Vega. And
Yeah, this was something I was curious about when you talked about it fracturing.
fracturing.
Yeah, that it's revolving. Well, I'll let you go on it, and maybe
Oh.
we'll run into it.
Okay, well, it's rising now in the east. This is about midnight. So it will be more prominent in the summer and the fall in the evening sky. But Vega is a very beautiful star. I think if I remember right, it defines the magnitude scale at
Yes.
0. So, and then they found brighter things. So we have minus magnitudes. But anyway, it's in Lyra, very easy constellation to spot, this little trapezoid. And I called this the once and future pole star because the Earth, as it rotates, it also precesses. And so right now it's Polaris, but it was once Vega, and it will be again Vega in about 12,000 years, I think. Now, this is the top of Mount Wilson, and they have a very interesting telescope up there. It's made up of, it's an interferometer. It's called Chara. This is one of its 1 meter telescopes. There's another one. There's another one. There's another one off up here. I couldn't get this to shrink low enough to get it in the single frame. And then this is the lab where they put the beams together and correct for their distance. There's another one there and another one there. So this shows 5. There are 6.
Okay, I didn't understand where these were. Now I get it.
Yeah. And there's a lot of stuff up there. The 60-inch telescope, which every time Tom says 61-inch, I think of this, but I shouldn't. And this is a big pond up there. This is the 100-inch telescope and the Chara office. But what this does is this gives a resolution of 3 microseconds, which is very, very fine resolution. And so they have looked at things like Vega, which are big stars, not too far away. And what they see is that it's hot in the middle and it's very cool around the edge. And confusing at first, they figured out that the star is rotating 12 and a half hours, one rotation. Our sun goes 27 days around here. So this guy is really ripping. And because of that, if it was going any faster, it probably has thrown off material at the equator. If it was going any faster, it would be throwing it off again to a debris disk. But it's swelling. It's becoming not a circle, a sphere. It's becoming an oblate sphere, and that the equators are farther away from the core where the fusion is. So these are cooler, and that's where this cool rim has. You're looking straight down on the head of a fat guy, and this is his tummy around there. So,
Oh, okay.
so anyway, it's pointed right at us along our ass. The Vega axis of rotation is pointed right at us. So we're looking down on one pole of Vega. And that's very interesting. They can resolve in heat difference in heat. They can see this in infrared. Now they've looked at other stars too, and this was very interesting. So this is Alderamin. It's got some bright spots. Beta Lyrae is resolved at 0.385 arc seconds. Altair, or Algol, I mean, Beta Lyrae's down here. Altair.
Yeah, that's another fast spinner, Jerry.
Yeah.
Yeah. I think it's 10 hours, isn't it? Something like that.
Something like that. And it's you can see its oblateness, but here they figured it out from the and it's cool around the rim again. But it's got a lot of hot spots. AZ Cygnus. Don't know what's going on there. The other one, we seem to be lucking out with looking at the poles of these stars.
Yeah.
And here is Beta Lyrae, the interacting Beta Lyrae, plural for Beta Lyra. CL, what is, do you know what lact?
Lacerte?
Lacerte.
The lizard.
lizard.
The lizard. Lacerte
Yeah.
is the possessive.
And they're resolving heat contours on it.
Wow. That's another down the pole, huh?
Yeah, it's
Oh.
it's we're looking down a pole, yeah.
Now, Jerry, you were talking about this fast spinning, and I thought that you kind of alluded to in the talking points that maybe that the stars were spinning so fast that they could actually fracture, to break apart, or is it?
Yes. Well, they don't break apart. Remember, they're not a solid object. They're like a fluid, like a droplet of water in a vacuum, in zero gravity. It's just sitting there wobbling. And if it spun real fast, it would start losing material around its equator. But it's not going to fracture apart. To get a star to fracture apart, in my mind, you need to try and zoom right by a black hole.
Yeah.
Then it'll take it apart.
And it's different than accretion.
It's going the other way.
Yeah,
Yeah.
the other way.
Yeah.
Now, accretion is on white dwarf. That's where something is losing it from its equator with the help of the black dwarf, or white dwarf, I mean.
Okay. Okay. Okay.
And this is A and B. Let's see what that is. It's in the caption.
Zeta Andromedae.
Yeah, Zeta Andromeda from September, done in September 2013. A shows the temperature of Zeta Andromeda as a certain type of projection, Ithoff projection. The contours represent 200 from 200K to 3,400K to 4,600K.
I wonder
And
if it's Merock, Jerry.
what?
I wonder if Beta Andromedae is Merock.
This is Zeta.
This is Beta Andromedae?
This is
Zeta
Zeta.
right there. Right
Oh,
there.
Zeta.
See,
Oh,
Zeta.
okay. I see.
Yeah. So let's see.
And then below, you're looking at different phase angles of some kind.
Yeah.
Mhm.
Yep.
Wow.
I don't understand something. How do they measure, like say that people say about our sun that it's 15 million degrees Kelvin at the center. But how do they? I mean, they don't stick a thermometer in there. How
Well,
do they?
nature has already stuck one in there for you.
Yeah.
So you just have to figure it out and interpret the data. But the point at which fusion occurs is known for hydrogen. And
Oh, okay.
when you reach that temperature, then you get hydrogen fusion. And
Okay.
it's definitely hydrogen fusion in the core. So when you can just do a little magnetothermodynamics and figure out how that works.
Yeah.
And then
And
what
from
the distribution is, a friend of mine did his PhD thesis on sound waves,
yeah.
the core being a mechanism to transmit energy from the core to the surface.
But they also let you do helioseismology and you get like a CAT scan of the sun. So you know the size of the core.
Yeah.
And so then from how the heat is diffusing out and everything, you can figure out these temperatures.
Yes. The use of supercomputers has greatly aided this whole field of astrophysics with plasma involved, magnetohydrodynamics.
There's that word again, plasma.
Yeah.
I struggle with that. I'm telling you.
It's just a big cloud of charged particles trying to work against the magnetic field that it created.
Oh my God.
Okay, this is the Great Bird Cluster, NGC 2301. It was suggested because it's by Astronomy Magazine because it was a cluster. And as shown here on March 30th tonight at 9 p.m., it doesn't have a moon anywhere near it although there is a faint haze down here. But you can actually see it in the sky. It's sort of goodbye to the winter constellations. And here it is a little closer in that region of Monocerotis with the winter triangle somewhere down here. I don't know what it looks like. So, and this is the Rosette Nebula, the Christmas Tree Cluster and Cone Nebula over here, Betelgeuse. And I don't know what this is, but Thor's Hammer is over here, M50. A lot of stuff in this area. And this is 2301, the bird cluster. This is a photograph taken by Pan-STARRS, and it's got some little black specks and stuff in it, which are uncontrolled overexposure, where one detector got so happy it shared its light with the neighbor, and it flipped the automatic gain control to read it as black.
Ronnie, you were saying something?
Oh, I just mentioned, he said bird cluster, and I'm looking for the bird look, the shape.
Well, you got wings up and down, maybe.
Okay. So not a lot of stars.
No, it's not a gigantic star cluster. Sure is, let's see, open cluster, fourth magnitude, spanning the Great Bird Cluster, or fully the Great Bird of the Galaxy Cluster. It was given this nickname by astronomy contributor Phil Harrington,
Oh,
yeah.
who imagines the cluster as a bird in flight.
Yeah.
It's more easily recognized in binoculars.
He was a great binocular guy.
Yeah. Yeah, he's a name I'm familiar with from my youth, from reading astronomy and stuff, telescope.
Yeah, I have one of his books on binocular astronomy. It's really nice.
Yeah.
He used to write a column in one of the magazines I've really enjoyed.
So I would say this is a contender for either it's a hawk, there's the wings, and there's the tail, and there's the beak, or it's a goose. Here's the neck, and there's the wings, and there's the tail.
Yeah. And if you turn it upside down, you're flipping the bird.
Also called the middle finger cluster.
Two chips.
Oh,
Flipping the bird. Uh,
fascinating
Look
stuff.
at this region. The Rosette Nebula is what I use to calibrate my cameras that have filters in them. So the filters are designated in the software as 1, 2, 3, and 4. And which is which, I don't know. You can shine a flashlight down there and look at it, but you get a reflected signal, and sometimes that fools me as to transmission. So what I do is I take a short exposure under each filter, and then I label one arbitrarily as red. And then I combine them all, and if the nebula comes out blue or green, I know that's not red. So I keep going around until my labeling one of them as red makes it red. And that's how I figure out what my filter colors are. Someone out there will know a much smarter way to do it, but that's the way I do it.
Put a
oh,
label on each one.
there's
Right in the
Hubble's
middle.
variable. Hubble's
I did
variable
that.
nebula up there.
I did that, and then I couldn't figure it out one time, and I was out with Paul Wynn at whatever that star, CalStar, and so he looked in there and looked at it, and it's real confusing at night. And then he said, "Well, you've got a spider's nest in here." Spider had gone in there and screwed up everything, and the web was all over, wound up. It had torn the labels off. So
Wow.
I try to
Question,
keep all my equipment capped when I'm not using it.
question, please.
Go ahead.
Does our galaxy have more nebula than star clusters, or the other way around?
That's a tricky question because it's got a lot more gas and dust. And if a human being notices it with his pattern looking for a brain, then it's got a nebula. But I don't know. That's
Well, look at the Rosette Nebula there. Would you say that's more nebula or more cluster?
yeah.
It's there's definitely more area of gas, but it's not as bright as the star clusters.
Nebulas can sometimes be an unfulfilled, not made yet star cluster. All the
Right.
gas hasn't condensed into stars yet.
Well, this one has condensed into the stars in its core star-making region, and it's got a big hole in it because these are hot young stars and they're blowing all the dust away.
Yeah.
So it's in the process of switching from being nebula dominated to star cluster dominated.
There's an interesting one up there, the Hubble's variable nebula.
Where are you?
That's right between the Rosette
Oh,
and
there,
Christmas
yeah.
tree.
Hubble's variable
Yeah.
nebula. Yeah.
That's the first, I think, the first image that Hubble took with the Hale telescope.
Oh, really?
Yeah, and it looks like a comet.
Yes, it does. I've seen it before.
Yeah.
Yes. And it dims and stuff because it's in a very dusty region and the dust moves back and forth in front of it. Not forth, but always,
Mm.
its light is coming through variable densities of dust.
And it's a young star. It's like a T Tauri, I think.
Right.
Oh.
Okay, well, that's it for today.
Well, one final question, if you don't mind. How in the world, I guess they have ways of counting in the Sombrero galaxy. You said moments ago, thousands of star clusters. They can see them.
Globular clusters, yeah, because they don't orbit in the plane of the galaxy, so they're up in that halo.
Oh, they're not inside. And
Well,
we
some
got
of them are.
You don't have to resolve them into stars to see that they're a globular cluster. It looks like a star, and you take a spectra of the star, and then you can immediately tell that it's a cluster and not a star, not a single star.
So the ones in the Milky Way are around the Milky Way then.
Yeah, they're spherically distributed.
That's
Interesting.
why they need a never-ending supply of graduate students to look at every single star one at a time. Oh, they have computers do it now.
Now, Jerry, can I ask one last question? you were talking about plasma. You said that it's charged particles working against the magnetic field it created,
that they created. Yeah.
that they created.
Because they're moving. Okay, so they generate a magnetic field. So there's a tug of war going on.
There's a lot of tricky things about magnetic fields that it plays with our sense of trying to think of easy ways to think of it. If you're standing still and an electron is zipping by you, you will feel the magnetic field of that electron as it went by. But if you are standing and the electron is standing next to you and it's not moving, you will not see any magnetic field. And if you zip by the electron and the electron's just standing there, then you will feel a magnetic field. So it's from your perspective, it's a time varying magnetic or electric field that is a magnetic field. So, I lost that train of thought.
Well, relating it to plasma, though, the plasma is
yes, when there's a magnetic field, the electron feels a force due to the magnetic field. So it's called a Lorentz force.
And that tries to deflect its path.
Yeah.
And when it changes its path, it changes its magnetic field. So you get all this interacting stuff going on with positive and negative charges flying around, and it gets really complicated.
This is going to take me a while to get this plasma idea.
Look at it this way. It's like a bullet trying to move through molasses. It feels the resistance of its medium, and it's the thing that created the resistance through its speed in that case. So it's not a real straightforward, simple, deterministic thing to do. It's complicated. It's an elegant extension of the three body problem.
Okay.
Well, of your four types of matter, solid, liquid, gas.
Actually,
your plasma is the hottest, wouldn't you say?
Plasma's the hottest. We have about 5 or 6 types of matter now that we want to get.
I got it anyway, but I know maybe I'm a little ahead of Tim Crawford. It's one of the few things on that I'm not going
to. Definitely are, Ronnie. I struggle with this one.
There's a lot more phases now too than there used to be.
Yeah.
Well, why don't you make that the topic of your December talk, Tim?
Okay, I'll add that.
No.
Plasma. We'll see everybody Friday night at our meeting at the museum with Dr. Malkin from UCLA taking us on board the web, and we'll see you next week for program number 267 of the Santa Barbara Astronomical